This is the slideshow video to tell you how to calibrate the FNN navigation for your robot, so it actually tells you the accurate information you want to know that your robot needs to know. So this first section will tell you how the program actually calculates the lines. And so what it is there's all the pixels. There's like the top left corner is 0, 0, the bottom right is 443 and 0, and then everything else. And so it measures the line points where you click, and then it stores the line points, and then it finds the length of the lines that connect it and forms a triangle, then uses the Pythagorean Theorem to find the length of the other one. And for those of you who don't know what that is, that's just a squared plus b squared equals c squared. And so it's just you add them all together and you get it. And then you get the final length of 3.1 revolutions, as you can see in the bottom. Here's the steps for calibrating your FNN navigation. So first you have to find out what your wheel circumference is. Ours, the ones we used, were 10 inches, but you have to find out the ones that you use so it works for you. And you have to calibrate your map image in pixels per inch, because if you just set it up to do random numbers, it's not very helpful. Then you have to find out what your revolutions per pixel are, because once again, you need to have the correct measurement to be able to go with the map. Then you have to calculate your 0-degree turn radius. This is pretty much wherever the wheels, like the line where the wheels connect. It's not really, they don't connect, but if you looked over it from the view, if you draw a straight line through the center of the wheels, that's your turn radius. It's a lot easier if you do, like, we drew out a little scale model of our robot. It's not perfectly to scale, but it's close. It helps a lot because then you can tell where the wheels are and how it's going to turn and everything. Also, you need to update the source code, which is included, and you need to recompile the code in Visual C++, which is free, and there's a way to download it. I'm not sure how. You can just Google it. And we will release future versions if we get enough feedback and enough interest from other teams, because it's a lot easier to re-update it if we know what people want. And so here are the different types of wheels, ranging from the smallest one to the largest one. We used the largest one, which is has 10 inches for rotation, and it's actually like 0.0999, so it's really close to 0.01 rotation. Like 1 inch is about 0.01 rotation, which is very easy to calculate. And so we need to determine the wheel circumference of the wheels. So there's two ways to do this. You can measure the circumference, as you can see on the left, which is just you place a tick mark and you roll the tire in a straight line until the tick mark hits the ground again, and then you measure that with a tape measure. Or you can do c equals 2 pi r or c equals pi d, which is just you take the diameter and then you multiply that by pi, which is 3.14, and you get your circumference. And as you can see, both of them were very similar. They weren't exactly the same, but it was pretty much up to the 1000th, 10,000th, it was the same, so it's good enough to just use whichever one you want. And then you have to calibrate your map image in pixels per inch. We used GIMP for this, but I think you can use the photo viewer editor thing that comes with computers. If you want to use GIMP, which is easy to do, just Google GIMP and there's like GIMP.com and you download GIMP. It's pretty much just like Photoshop, only it's free source, open source. And then what you do is you simply, in GIMP at least, you just put your cursor wherever you want to measure the pixels, and it'll tell you the pixels of wherever that is. So as you can see, the base is 200 pixels, and then conveniently it's 200 inches. So it's very easy to calculate that. It's pretty much just 1/10 of an inch is a pixel, so it's 10 pixels per inch. This is also, the conversion is found in the open source code. And then you have to calculate the revolutions per pixel and the revs per inch, which is just revolutions per inch times the inches per pixel, which is not very hard to do. And then you have to calculate the 0-degree turn radius. The way we found it easiest to do is, what we did though on a robot is, as you can see, when you open the program, you have the little robot thing. There's a line through the middle of the wheels. Like I said earlier, that's the turn. That's like the center of the turn. It's a lot easier, and it helps a lot to know where the turn radius is. Like if your wheels are in the front of your robot or in the back of your robot, the turn radius is going to be in the middle of the wheels, like the middle of the axle. Of course, if you have 4 wheels, each are driven, even though you can only really have 2, but if you have 4 driven wheels, the turn radius would be like in the middle. And so the turns happen when like both wheels go in opposite directions. So if it's just a one wheel's turning, this isn't going to work because the turn radius would be the other wheel, or the other side of the robot, or the other ground touching point. But when they're both spinning, it makes the turn radius in the middle, and the way you calculate it is, not the way you calculate it, but you program the robot's wheels to move 1 revolution in a turn, then you just measure how many degrees the robot does turn. We found our robot turned about like 225 degrees, and so then we used farther calculations to, like, a complete 360 would turn it into 1.36 wheel revolutions. And then here is where you would update it. The distance is the double rev length equals C1. C1 is the Pythagorean Theorem, as you can see. C1 equals square root of double C squared. But so, C1 times whatever your revs per pixel is, and then for the turns, it's revs per degree, and that's just 136 divided by 360 if you're using the big wheels. The 136 is just how many revolutions it takes for your wheel. So substitute 136. 136 is pretty much a variable. Take the amount of revolutions it takes for your wheel to complete a 360 degree turn and divide it by 360. And for more information, go to the website where you should have downloaded this program from, which is codeplex.com, FLL and XT navigation. Thank you for using our program. I'm Silent Striker. Have a nice day.